Good morning. Class starting? Yeah. Good morning. Can you hear me?
Morning.
If you notice me freezing or getting bumped off completely, just hang in there. I'm having major crashes that are hard to diagnose here for 2 weeks now, and I will switch over to an iPad. So just wait for me. I'll be back if that happens. I just did a restart of the computer, hoping to forestall it. We'll see how that goes. Okay, we're in the topic of confidence intervals. Who missed Monday's class completely? Jade, were you there?
No, I was not.
Okay. You should, as a background, do some Googling around to learn what a margin of error is. It's the same thing as a confidence interval. So, to review
Okay.
very briefly, when we look at polling data and we see that the likability score right now for Trump, I think, is like at 37%. You'll notice a little bit of text somewhere in that report, if it's a visual especially, that says margin of error 4 points. And what that means is, okay, the mean is 37%, but since we just sampled people and we didn't get the whole population, nobody asked me, for example, nobody asked any of you here, I'm sure. So we don't have everybody's answer. So we can't be sure about that 37%, but we can be 95% sure that the real answer is somewhere uh, between 4 points below and 4 points above. So from 33% to 41%, somewhere in there, we can be 95% sure is Trump's likability score right now. Does that make sense?
Yes.
That's what we're talking about. And then from there, it's just the math to how to get that. So one of the problems is we need to know how sure we want to be. And there's data that we need in order to be able to do it. We need to have a group, the sample size, we need to have the sample's mean and the sample standard deviation, all of which are really easy to have if you're sampling people, right? And then there's software that they're doing to compute their 95% sure margin of error. But I'm showing you how we do it by hand, tying it into the idea of a z-score, right? We come up with the margin by basically using the same formula as we use for finding a score if we know a z-score. So we're going to not use z-scores for this, but as you recall, folks, we're going to use t-scores. So you're going to need your t-table, which means I too need my t-table. Give everybody a moment to find it and get it up on their screen somewhere so that you can all participate. It's up on Canvas, Jade. I think I put it up on Canvas in a confidence intervals module. I'm pretty sure that's what I did. Our formula is going to require us to find a t-value, and I'll go over how we do that. And it's going to require some more of us than just that. I'm going to switch over to using my screen here in a minute, but I want to pose a different problem than the one that we had before for us from some old problems that I have here. And then I have more. So basically, we're just going to run through some, going to make sure everybody's up to speed on this. And then if people are and they're comfortable taking a quiz on it on Friday on their own, then you're free to leave once we cover. Once you think you know this stuff, you don't have to stick around. But I will stay the entire class time for people who want any kind of catch up lecture or asking questions. Now, I'm going to do this once free for anybody who wants it, no matter whether you were here or not for what you missed. However, after this, I will only be entertaining questions like that from people who actually showed up for the lecture. Okay, so I'm not going to reteach the lecture, but today I'll answer any and all questions whether or not you showed up for something. We're going to be building from this idea a little bit, so you want to make sure you understand it. You're going to see confidence intervals a lot in professional literature. When I was at your stage and as an undergrad, there was none ever reported. By the time I graduated with my PhD, still none. But that was in 1992. And all through the 90s, never saw them. About 2005, so for the last 15 years, there's been a little bit of a push toward confidence intervals. In the last 3 years, it's exploded. So now I don't think that you can actually get published without including a confidence interval for all of your means, right? So it's important that you understand them. Also for when you're reading articles. Okay, let me do one more time a concept that's part of all of this, and I'll do it so that it's not in the middle of a problem. Give me a second so that I can do screen mirroring here. Okay. And the concept is degrees of freedom. I need something like in between these two lines. Is that, oh, wait, okay, hold on. I found a miracle. Hang in there, you guys. I found this cool slider. Look at that. Okay, now I can be a real teacher. All right, degrees of freedom. Degrees of freedom, you should have this in your notes from yesterday, from Monday, are the number of values free to vary in a group of numbers given certain restrictions on the data. I'll say it one more time. The number of the values that are free to vary within the group of data given certain restrictions on the data. So when we are going to be computing t-scores, we need to know degrees of freedom. And the data that we are going to be using is a simple list of numbers that we don't have to see. Well, I'm just going to give you the restrictions. We're always going to need n, the mean, and the standard deviation. So given the restrictions on the data that we have, and actually it's just n and the mean that are important, we are going to set the size of the group and we are going to set the group's mean. And then we're going to see how many values can vary. I'm going to say that we have 3 numbers. And so that makes n is equal to 3. And I'll make a mean 100. Hey, Isaac, give me a number, any number from negative 1,000 to positive 1,000.
45.
You got the echo bad. 45 it is. Jade, give me a number.
62.
Thank you. None of you guys ever give negative numbers. All right. So we have n set. We have the mean set. I can't just pick any number I want for this last one. If I do that, I won't necessarily get a mean of 100. I have to pick the number that when I add them all up and divide by 3, I get 100. Right? So 100 equals 45 plus 62 plus that question mark over 3. That's the restriction on the data right there. Only 2 of these numbers are free to vary. The third one has to be locked in order so that these restrictions remain true. Okay, does anybody have a question about what degrees of freedom is? All right, I'm going to expand this a little bit. Let's say I have 30 people in a study. How many of their scores could vary if I know that there's 30 people and I happen to know the mean? How many out of 30 could vary before we have to adjust the last one?
29.
Thank you. I just said the answer out loud. Thank you, Elijah. Okay, so basically degrees of freedom, when we have these restrictions, sometimes written small letters, equals n minus 1. Whenever we have the restriction that we know n and we know the mean, the degrees of freedom is always going to be n minus 1 for one group. Okay, that's a concept, degrees of freedom. That concept gets used to find the t-value that we need in a formula. The t-value for confidence intervals. Here's the formula for the this top line is the formula for the 95% confidence interval, and it's got a t-value in it. I'm going to grab this thing and put it on a new page for us. How do I get to say paste? Anybody know? No, you can only use it on one page. Fine, we'll redo it. Okay, so the 95% confidence, 95% confidence interval, CI 95 equals the t-value of 0.05 times, this is known as the standard error. There's a plus or a minus here. Add that to the mean. I'm going to clean this little bit of a mess up here. Make it a little bit easier to see. Okay. The 95% confidence, 99% confidence interval. All right, so we have almost everything that we need to solve this problem if we know n, the mean, and the standard deviation. But here's the problem. You don't really know what this is, this SX bar. Like that's a new concept. It's called standard error, and it's equal to the standard deviation divided by the square root of n. So this is going to give us two numbers. This is going to give us two numbers. It's going to give us the number when we get this stuff in the bracket and subtract it from the mean. That's that negative sign. And we're going to get a top number when we add that mess to the mean. That's going to give us a low number, which is going to be less than the mean. A high number. That's our margin of error. That's our confidence interval. Notice that this is a lot like when we just wanted to find one score with z-scores. So we were looking at scores compared to a group mean within one group. Now we're looking at a sample compared to a population. You might actually understand it better if I substitute right here maybe this will help. We are looking for the margin of error around this theoretical mean because we're trying to figure out the population mean. We don't know it, but we can come up with a range within which we'll find it. Well, at least we'll be 95 or 99% sure we'd find it. Okay, so notice this is a lot like what we did before, where we wanted to try to figure out a score if we knew the z-score, the standard deviation, and the mean. That's the old formula from z-scores. Notice it's got the same format. It's like, so instead of z, we have t. Instead of the standard deviation, we have the standard error because we're working with a group instead of an individual. And plus the mean stands. Okay, so what we're doing is we're substituting in t-scores for z-scores and standard errors for standard deviations. We're taking it from one person compared to their group to a group compared to a population. That's basically why we need these new things. Okay, I'm going to erase what's not a formula. So that way I have room on the same page here. We already computed for a set of data the 95% confidence interval, but to review, instead of doing that one all over again, you already have it in your notes. I want to do the 99% confidence interval. So that's this one right here. Oops, hang on. That's this one right here. Okay, so here's what we have. We have, we'll use new numbers. We have a group of 10. And they took an aptitude test for doing work with spatial skills. And the scores can range from 1 to 10 or 0 to 10. And their mean, the group's mean, these 10 people's mean was 5.5. And their standard deviation was 0.25. Some nice round numbers to work with. So we have that group, and somebody comes up to us and says, all right, what do you think the average person out there, what would their score be? And you're like, well, I have a sample of 10. I can extrapolate from my sample of 10 and give you a range, otherwise known as a margin of error, otherwise known as a confidence interval. I can give you the parameters within which the average person will score. How sure are you about that? Well, I can set it up so I'm 99% sure. Will that work for you? Yes, thank you. Do the work. Now you're making some money doing your statistics. Congratulations. So we're going to use this formula that's got the green there at the beginning to find the 99% confidence interval. Why? Because we promised the customer we can do it to 99%. Or because it's something really important that we want to do and be very, very sure we know the answer. So we pick 99% instead of 95%. Okay, so how do we set up this formula? We say CI 99 equals plus or minus, leave the T in there for now, times, and then it's the standard deviation over the square root of n. So it's 0.25 divided by 10. Oh, you're welcome for that, by the way. And we're going to add that to 5.5.
Isn't it?
Is Sam here?
Yeah, isn't it? Oh my.
Can you hear me better?
Yes, I can hear you.
Huh. Okay, Isaac, what's your question?
The square root of.
He wants to know if it's the square root of.
Thank you, of 10. Isaac, thank you. Good eyes. The irony of not being able to be heard when you have the saving information is rough, isn't it? You're like, but she needs to know this. Okay, so let's just get that 0.25 over the square root of 10 and just get that done. So we have plus or minus t times 0.01 times, somebody tell me what you get. What'd you get? Is anybody using their calculator?
I got 0.079056941.
Stop. Yes, and we're going to round that to 0.08. Thank you, Jade. That's the right
You're
answer.
welcome.
0.7986523427. Okay, 0.08 plus 5.5. We still can't do anything because we need this t. So now we have to go to a t table to find it. Here we go. Oh, you know what? We have to stop. I'm not going to stop sharing because I'm going to talk you through this. You're going to look at your t table. I'm afraid that it's going to crash if I try to move around too much. So we know that we want the 0.01 column because that's what we said when we said we do a 99% confidence interval. The 0.01 columns means we'll be 1% unsure. We're 99% sure. We're going to make an error 1% of the time. That means every 100 times we try to do this, we'll be wrong once. Not bad. Okay, so we know we want the 0.01 column, which is the furthest column to the right. Those are all t-scores in that column. We need the t-score. But what we don't know is how far down to go. We determine how far down to go by the column all the way to the left, df, for degrees of freedom. And df for a list of numbers, when we know the mean and the n, is n minus 1. N is 10. So we take degrees of freedom down to 9. We go across to the furthest right column of 0.01. And we get a t of 3.249, etc. We're going to call it 3.25. Who doesn't understand what we just did to find t? Very important that you say so. Okay, so now we have plus or minus 3 point, what is it? What did we say? 25?
Yeah.
Thanks. 3.25 times 0.08. We get that. And we add that to the mean. And we do it. We get it. We subtract it from the mean. And then we also add it to the mean. This is what I mean by that. This and this. Okay. So 3.25 times 0.08. Somebody put us out of our misery and do the math. Don't make Jade do it.
It's 0.26.
It is. Thanks, Elijah. Okay, so 0.26 plus or minus 0.26 plus a mean. All right, here's where students usually go wrong. They're usually fine right up until then, and then they're like, what do? I know I'm supposed to have two numbers. That's how we write our answer. But where do I get these two numbers? You get it by subtracting 0.26 from the mean to get the low one and adding 0.26 to the mean to get the top one. Okay, what are those numbers?
I don't know if I'm the only one, but I can't see what you're doing anymore.
Same here.
Really?
Yeah, there it is.
Yeah, but it won't stay.
Oh.
Hold on. You could see the last line though, 0.26 plus 5.5.
No, I can't see anything past the 0.25 over 10 squared plus 5.5.
What? Why didn't you say something 3 times ago?
I thought I was glitching.
No, it's apparently it can't see the whole screen. Hold on, maybe I can get you to see some of it. Can you see any of it now?
I can see the 3.5 times 0.08 plus 5.5. That's
Got
the
you.
last one I
Okay.
can see.
There's a line below it. We're just going to carry on with that line. Hold on.
Carry on. She said.
So
Not
CI,
legit.
you can see this now, right?
Oh, yeah. Okay, there it is.
Plus or minus 0.26 plus 5.5. Can you see that?
Yes, I can see that.
Okay, we're there now. So CI 99 equals some number less than or equal to the population mean, less than or equal to some number. And that's the margin of error. That's the confidence interval. How do we get it? This is where most students fail. They get this last line right here, but they can't give it to the answer because they don't really know what they're doing. We're trying to come up with the range of numbers within which we can be 99% sure is the population mean. And we do that by subtracting 0.26 from 5.5 for the low number and adding 0.26 to 5.5 for the top number. That's what that plus and minus means. It means you're going to do 2 operations. You're going to subtract it, get that number, and you're going to add it, get that number. So what are these 2 numbers?
The low number is 5.24, and the high number is 5.76.
Yep. Anybody need help getting those 2 numbers? Hey, Grace, how you doing? You're quiet today.
Oh, I'm doing good. I'm
Yeah?
just like trying to write everything and
You're
stuff.
just cruising through getting your notes done? I think that's a good place to be. Okay. So what is this? This is the answer to the question. You put this down. If this was the question, you get 100. So what does this mean? What it means is that when I have a sample of 10 people who had a mean of 5.5 and that standard deviation that they had, that I can then compute you an interval of numbers, a range of numbers. And I know that I'm 99% sure that the actual population mean, the real one, not my sample of 10, but all the people in the group, everybody, that the mean is between these 2 numbers. We never know that our sample is exactly the same as a population. We never do. When people are doing polling for politics, they're not getting everybody. They're getting some people. And they're hoping they get the type of people that represent everybody, right? And then from there, if that was true and they did a good job, then you can make good estimates about what the population's mean is. But you can't be exact. 5.5 is between 5.24 and 5.76. The population mean is also between 5.24 and 5.76. So in the little video that I showed at the beginning of the class on Monday, it was about should baseball season start, I think. And she was showing you that she had different samples all around the country and we needed to know the population. She mentions very briefly that the more people you can have in your sample, the better you are at computing this margin of error. You'll become more accurate. And here's why that's true. It comes down to this part of the formula, the standard error part of the formula. S over the square root of n.
You're getting to where I can't see you anymore.
Something's really wrong here. Is that better?
Perfect.
Can you see down here when I do that? Can you see scribbling?
I don't see what you're doing.
How strange. All right, hold on. I have an idea. Somehow or another, it's taken this window. Is that better?
I can see the scribbles.
Yeah, it's odd. It's sharing my pad screen, but on my computer, that window was down really low. Even though it's supposed to be sharing the pad, when I raised up that window, now it's showing everything. That's odd. I thought it was just paying attention to the iPad. Someday I'll understand all of this new tech stuff and it'll change. Anyway, the larger N is here, the more precise this number becomes. So we can become more sure of a smaller range. We can become more and more and more accurate, the more people that are in our sample. And this is true not just of the confidence interval problem, but of any time we're trying to make inferences from a sample to a population. That's why you'll hear when you go to experimental that you should try to have 30 people in a group. If you have 30 people in your group when you're doing these various statistical tests that we're going to be doing after this week, then that's a group size that's adequate to be able to predict from. Smaller than that, and it becomes less useful to predict from. So this little sample size of 10 wouldn't be great. I use the number because it's easy to divide by rounder numbers, that sort of thing. All right, let's do another one. Let's do another one where we have a group of 10 because I just happen to have that problem right here. Okay, these are 10 students who are living in the dorms on Elmira College campus right now, and we get their happiness score. This is going to be your project going forward for the end of the week. I'm going to give you a quiz question answer so that I can see that you can just plain out do it, but then I'm going to have you survey people and get their confidence interval, because your calculator will give you the mean and the standard deviation, and you can use those to do what we've been doing here. All right, so we got a sample of 10 people, EC students. So N is equal to 10, and we get their happiness in score. And let's say that the scores could range from 0 to 5, and we happen to pick a bad day, and our happiness score mean was 1.46. Very bad day. The standard deviation happened to be 0.34. Whoa. Okay, question. What is the 95% confidence interval? And as I say, also in other situations, you might be getting asked, what is the 95% margin of error? It's the same question. So 95% confidence interval has a formula like this. I'm just going to put it S over the square root of n right in there. Try to substitute the numbers in there, folks. Start with that. Tell me something. When I do this, are you seeing my Wow. It's done something to the t-table. This is the t-table. Can you see this on my screen? With a document in front of the formulas, or do you just see the formulas?
We just see the formula.
That's good, because it took the t-table and it made it this tiny little thing that's like a 1/4 inch wide and really tall with no numbers. Back. I believe I've got the right numbers in place. Am I correct? I don't have the answer to this problem here. Oh, wait, I do. I don't have the steps, though.
I got the low number
Yeah, what'd you get?
being 1.21,
Yep.
and I got the high number being 1.71.
Yeah, so do I.
I got the same.
What's this number, just so we have it here written in for people's notes? What's this number that the left side becomes 2.26 times 0.34 over the square root of 10? What does that turn into?
0.25.
Thanks.
Yeah, 2.5.
Thanks. I don't have the steps here. I just have the answer. Okay. Now, we're going to compute the 99% confidence interval for the same one. So let's say that we're not content being 95% sure, that we know that most college students' happiness, we can be 95% sure that the happiness rate then was between 1.21 and 1.71 of all Elmira College students, sorry. So it's a range instead of an exact number. We can be 95% sure. Let's see what happens when we want to be 99% sure. So change the t to t of 0.01 and everything else stays the same. So I'm just going to do some careful erasing here.
I got the high number being 1.82.
Anybody else? Because I don't have this. I need
Yeah,
to
I
try.
got the same.
Say it again. 1.82.
Yeah. And then the low number, I got 1.1.
Anybody else?
I got the
Heather's
same.
like, yeah, that's great. Okay, so the 99%, I should have left the 95% up. So 95 was 1.21 less than or equal to mu less than or equal to 1.71. Okay, let's just look at the difference and understand this. If you want to be 95% sure that the population of EC students mean is captured by your data, then you can say that their mean is between 1.21 and 1.71. But let's say that instead we want to be 99% sure. For some reason, doesn't matter. 99% sure. Notice that the range has to expand. If I want to be really sure that I captured it, I have to go bigger. It's just like, think about like you lacrosse guys. If you want to get the ball into the stick, it helps to have a bigger net. This is the exact same thing. I have to cast a wider net if I want to get 99% of the fish. I have to cast a larger range if I want to capture 99% of students' answers, rather than if I'm being content with just 95% of students' answers. Does that make sense? Right, so when you're 99% sure, you need to be, you have to end up with a larger range, which doesn't help a lot because sometimes the range is so wide that it becomes meaningless. Like, let's say that the president's approval rate right now was 45% with a margin of error of 6 and a 99% margin of error of 6. That means that we don't know whether 51% of people like him, which could later turn into a win, or if only 39% of people like him, which isn't very high. Like there's a huge range there that ends up becoming not that helpful. We don't usually need to know 99% to be comfortable with our predictions. We often can just go with 95%. In some fields, they're happy with just going to 90%. And that's why the T-table has that first column, 0.10. Right, so there's one field, I don't remember what it is, that used to have their confidence intervals be at 80%. That was very exploratory work. They just wanted to know whether it was worth continuing on. Are we getting 80% of the results we predicted? Yeah, okay, good enough to keep funding the research. In psych, we always want to be at least 95% sure when we say something, because our things end up turning into diagnostic criteria, medication levels, whether or not somebody is going to be considered to be a criminal in a jail, or a psychotic in a jail, or somebody who doesn't need the jail hospital wing. They can just go straight into the general population. Like, we have huge consequences, huge, whether or not a kid gets put into the gifted and learning thing, what colleges you get into, gigantic consequences. So we want to always be at least 95% sure when we make predictions about populations that we're right. And sometimes 99%. And I'll talk more about that when I talk about the actual statistics that we do when we want to compare a group to a population to see if there's a significant difference. And when we want to compare two groups to each other to see if there's a significant difference. And when we want to compare one group pre-test and then do something to them and then post-test. In the next few weeks, you're going to learn all of those three types of analyses. You're also going to learn about how to do correlations. And then if we have time, you're going to learn about something called chi-square, which is just head counting types. So there's not a perfect even number of people who said yes and who said no. Is there really a significant difference there? Or is it close enough, like that? But for now, we're just setting that all up with confidence intervals. And so here's what I think we should do. I'm going to give you a confidence interval quiz. It's going to have like a couple of actual problems, just so that we can see if you can do what I've actually covered in lecture. And then I want you to take it one step further. Let's find out just how miserable campus is. So you have to, wait, Heather, I don't know if this works. Who else is living off campus right now? Wait, let me put this another way. Okay, got you, check. Who cannot have access to 20 other Elmira College students? Who can't access them? Think social media, texting. You don't have a way to reach out to 20, Jack? Could you do 10?
20.
What?
I don't know 20 people.
Yeah, exactly. That's what I was thinking. So how about 10? Could you get 10?
Yeah.
Okay, because you can also ask your friends to ask. Don't forget, if you really get stuck. Heather, can you get 10?
I'll make my husband ask them when they're training.
That's perfect.
That works. Yeah.
That works. That's
Okay.
what, will they be able to get you that data sometime before Monday?
Yeah. Isaac and Sam can answer if they go up there too. So
What
it'll
training? Oh, this is physical. Yeah, gotcha.
just the athlete training. Yeah.
Yeah. Everybody else, can you get 10? Tell me now if you can't.
Totally.
Sounds good. Okay, here's what we'll do. Every one of you has to ask 10 students on a scale of 1 to 10, how happy are they? Right then, that minute, when they answer. How happy are they? Don't talk about COVID before you ask them. Don't talk about anything before you ask them. Just throw it out there. If you're going to use, like, I don't know, whatever thing that you use now that's not FaceTime, or I'm not sorry, Facebook or not Facebook, ask that way. I don't know if people ask stuff like that on Instagram, but you could just grab your contacts list and send it out, whatever you're going to do. Okay. I personally would just text people myself, but you're going to get 10 answers. So N is 10 for you.